Thank you. My name is Rob Simmons. My handle on most things is Utkanos. It's duckbill platypus in Russian. Long story. Ask me after the talk. I am formerly of ThreatConnect. I was the Director of Research Innovation, and now I'm an independent malware researcher. I'm working on a number of things, and you'll see some of my work in towards the end of the talk. Actually, throughout the talk, but some of my latest work is towards the end of the talk. So today I'm going to cover some techniques and methodologies for comparing unknown files, comparing malicious files, suspicious files, and there are a number of problems in this area. So I want to talk about some of the problems first, and then talk about some of the solutions that I might have for them, and some of the techniques that I have for getting information in these different ways. So first off is the AV problem. I think everyone is probably familiar with this, that if you have a particular file, and let's say it is malicious, let's not say it's a false positive or something like that, but if you have a malicious file and you submit it to a number of different AV scanners, you may get different results from each one. You may get similar results from some of them. And then on top of that, the nomenclature that they use when they actually detect something that isn't a generic signature, the nomenclature that each one of the AV companies use is quite different. Each one might have a different name for a different malware family. Some of them have their own internal codes for them and stuff like this. So you have a problem if you're going to use AV to figure out what it is you're looking at. But I do have a halfway solution, because you're working with pretty bad data to begin with, but I have a couple ways of making it a little bit better, but not great. And then another one of the problems with the nomenclature comes from a different source. And so this is the marketing problem. And so marketing departments want to brand the malware families that that particular company has discovered or identified. And that's how you end up with pandas and rocket kittens and kitten rockets and panda bears and bear pandas and that sort of thing. I am picking on one organization there, sorry. So you may know, if you see one of these that you recognize, you may know who this is, but all of these are approximately the same threat actor group. So which of these do you use? So this is, this kind of compounds the AV problem that you have with sort of a marketing problem. And this problem is more, there's a social aspect to this, where there's the need for fame for individual researcher, and then there's the need for marketing and eyeballs and clicks for a marketing department. So both of these are kind of pulling in the wrong direction if you want to identify a particular file as belonging to a malware family. So I can also break this into a couple of different job roles that we might have. So you have the researcher's problem. The researcher's problem can be summarized as, what am I looking at? So I have a particular file that I've collected from a collection system, or someone has given me, or something like this. And I need to know what I'm looking at. One of the other questions I need to answer fairly early on is, can I relate this to other samples? And when you're doing that, you really want to find out if someone else has kind of identified this particular malware family. Is this something new? And if it's something new, then it's something I really want to spend more time on. If it's something that someone else has done a lot of work on, kind of check what they've done, and if I can improve it, that's great. But if it's not, if it's something that's well known, move on. And then this is a related problem, but the job is different, so the reasons for why they need to answer these questions are different. So you have the incident responders problem, and they also want to know what a particular file is related to, but the reason they need to find out what a file is related to has a different motivation. So the motivation here is, can I find previous work around this malware? And the reason they want to find previous work around this malware is because their hair is on fire, they have people breathing down their neck. There's a security breach that has occurred, and so they actually want to take the fastest pathway to knowing what it is that happened that they possibly can. So finding related files and then pivoting from those related files to previous research can accelerate the incident responders process. So each of these general problems have some related solution methods. So for the identification problem, what you need to do is determine the malware family membership of a particular sample. This is not always possible. So my training from college is biology, and so I like to think of certain things in that way. So if you think about from the bacteria or archaea level, they have horizontal gene transfer. So it makes identification of certain things kind of difficult. And so you have kind of the same thing. You've got threat actors and who are programmers, and they're sharing code horizontally across malware families. And so you may have problems identifying a particular malware family. So it is difficult. And then this problem is a little bit easier because it's a little bit more structured. So locating associated samples. So within a body of samples, if you've got a malware library or repository of some kind, within that set of samples, can I find samples that are related to the one that I am investigating right now as a researcher or an incident responder? So there are a number of techniques that I'll cover for both of these questions, both of these avenues of analysis. So the first identification method I'm going to cover, this is kind of the low-hanging fruit, and also, like I said earlier, the data that you get out of this system is not very good, but I'm going to cover one of my methods for at least improving the data that you're working with. It's still not going to give you super accurate results, but at least they're going to be better than you were before you implemented this particular procedure. So one of the problems you'll notice when you run a file through multiple AV engines is that certain companies share the AV engine. They share the engine among each other, and so if you're looking at an AV scanner bank and you've got X or so many scanner engines, and you're basing your weighting, you have weights on how many times a particular word or malware family comes up across your AV scanner results. If you're weighting them, you need to know which of the engines are shared across the AV scanner companies. Because you need to know that should be weighted as one scanner result instead of 5 in this case. So you run this particular sample, and you'll find AdAware, AlYac, Bitdefender, Emisoft, F-Secure, GData, MicroRolled, eScan. All these have nearly identical scanner results. And I picked this one, so they are generic. It comes back as generic, but they have that sort of, who knows what that number means at the end. I don't work for any of these companies. It's probably intellectual property. But I do know that that's a very unique number across all of the various AV scanners. So it's a pretty good indication that they're sharing an engine. So there's a force at work here inside of the companies, and me as an outsider from AV companies, I don't know the details of it, but from people that do work in AV companies, there's kind of two forces at work here. If you make a generic signature that blocks as much malware as possible, that can actually cost your company less to develop that signature than going granular by malware family and having a detection that tells the end user what malware family it is. So these two signature development methodologies kind of I think are pulling at opposite ends. So you've got a generic signature, and then you have a specific signature. My beer choice here is probably not as amazing in this area because I first gave this talk in Serbia and then in Croatia, and so they were like, ooh, new beer that we've never heard of before. I hope everybody's heard of DC Brau. Okay, so one of the other things that that I hope you take away from this talk, by the way, is some of the vendors that I think have usable results. So they get fairly granular in the results of the malware family that they're detecting. I think, and most people that I've spoken with agree that Microsoft, when it does detect something, is very, very good at being accurate at what malware family it is. But they also, they are one of the culprits, I would say, in the AV nomenclature game, because they've got their own name for nearly everything. Unless it's super popular, but they've broken everything down into these very small granular malware families. So it's valuable, but it also adds a level of confusion. ESET, Kaspersky, Sophos, these are others that have fairly accurate, at least usable, non-generic results for many unknown files that you submit to them. So this is the process that I use to kind of boil down results from a pile of different AV scanner results from varieties of scanners down to just a few scanner results that you can kind of look at and at least include in your further analysis. So this file submitted to this variety of AV scanners. So a lot of them come back with a variety of different strings here. And you'll notice that this is not the full list of AV scanners that this was submitted to, because one of the first things you need to do is just remove all of the clearly generic results. If it says something like generic, toss it, because it's not really identifying something for you. Even if it has one of those unintelligible numbers at the end, you don't know what that means, so toss all that out. Also, be careful about some of the sneaky generic results. If it says it's Zeus, it's probably not Zeus. It's probably a signature that covers a lot of descendants of Zeus or related. They might have had code snippets because the source code was open source a while ago, or leaked. I don't know if open source is the right term for that. And then Zbot, Zeusy, all these sorts of things. You want to look for those generic results and kind of remove them from your data set. So what you want to do is take those results that you see as being the same shared engine. I am counting Emisoft as the same engine because that unintelligible number that's there matches up with the other ones. So they're just adding their own little, little sugar on top of the shared engine. Down here, we've got another one, Avast and AVG. So those are two identical shared engine results. And so what we want to do is kind of collapse those down and count them as kind of one vote, right? So after collapsing it all down to one vote and kind of removing stuff that doesn't really have any valuable strings in it, and by the way, this is not a precise thing. This is kind of throwing darts at a board. I'm just kind of boiling the stuff down into what is possibly usable from the data set. So we've got 3 votes for Simi and 3 votes for this thing Isbar. So we're going to call these kind of the same. So I'd call them, maybe 1.5 votes. I don't know. And so we're going to say maybe this is Isbar, a little bit more towards Isbar, a little bit less towards Simi from the data from AV scanners. So this might not be true, but it gives you 2 strings that you can go Google and see if someone has done any research on this particular thing. And if you go back a couple slides, I've got some of the malware encyclopedias. You take this string, go to those vendors that you see are returning it, and then take a look at what information they might have about the sample that you're looking at. So another method for identification what malware family something is Malpedia. This was announced, let's see, it was 2017 in December at BotConf. I think it was already running by that time, but they announced it at BotConf. The idea is great. The idea is really awesome. It needs more people contributing work to it, contributing more samples, contributing more signatures, identifying more malware families. I went and corrected some of my slides and boiled them down a little bit, but I feel Space Rogue over my shoulder going, that's a terrible slide. So Malpedia basically gives you the ability to take a file, submit it, and then it runs a series of Yara signatures. So if you're familiar with Yara, Yara is a signature system which takes a signature and it looks like C code a little bit, and then it looks for strings and then conditions of how those strings are related if they're found. That's a simplified version of it, but it's basically for free-form signatures that you create yourself, or you can get, there's repos of them, GitHub, there's various organizations that share them, but Malpedia is based on Yara signatures. So there's basically a malware family where experts in the malware analysis and reverse engineering community and industry agree that this is the best guess as the identification for this particular piece of malware. There are signatures for that. And so you submit something, and then you get back like what the percent match is on strings matched, is it a true match, et cetera, et cetera, et cetera. So it'll give you the rule name, which will have what Malpedia thinks is the malware family. This does still need to hit critical mass. And so I encourage you guys to use it, submit samples, join the community, and advance the cause. Another identification method, so throw a plug in for my old shop. So this is the free version. It's got a lot of nice bells and whistles. Take a look at it. But this is actually a project that my team put together. So it's called the Technical Blogs and Reports. Sounds a little bit boring, but what it is it's essentially an RSS reader that goes out to any blog that has malicious indicators in it and is an RSS, and then pulls all of that data in and puts it in one place. And because it's all open source data, this is part of the free tier at ThreatConnect. So you can go through and see, all sorts of different threat data and pivot around in there and potentially identify something. This is just a screenshot of hop2.org, which is a dynamic DNS, which is popular with a lot of adversaries. And so if you've got one of these, if you've got a host here, you could search for that particular host and pivot around to the malware family and other data. So I always want to include this sort of thing in here. So there is a good identification method. Don't forget, just Google it. And I love the mandatory XKCD of how to become an expert in computers. And it's basically go through this thing, but actually down here is Google the name of the program plus a few words related to what you want to do, and then follow any instructions. So always go and check Google, basically Google all the different things that you're working on. And then I had, over the course of the time I've been giving this talk, a couple of people have pointed out some other systems of identification and classification that some of them I was aware of, some of them I was not. And so I've kind of gathered all of those together. And so some of you might recognize a few of these: common malware enumeration. So this is a MITRE project. MAEC, which is a subset of sticks. And this is, both of these are, fairly accurate, not accurate, but fairly maintained. ICAR has had, I'm not sure about the status of it, but ICAR had a nomenclature system. The wild list is probably one of the oldest nomenclature or identification classification systems, and Caro as well. But the one thing that you'll notice with all of these classification systems, they have something that's very missing from the classification systems that the AVs use and the companies with marketing departments. So there is a need there that these classification systems don't satisfy, and that is the fame, like the need for clicks or the need to be famous. And as a biologist, put my biologist hat on from college, that problem was actually solved in biology. I don't know how to implement this. I'm not really sure how to implement this, but the Latin naming system in biology satisfies both requirements. So it is a structured naming system like the systems that I just showed you in the past, this slide. It's a very structured naming system, but it also includes the ability for the biologist that finds that new species to leave their mark on the world and become famous through the naming system. So I'm not sure how to implement this. I'm not sure who should control the system, but at least if you implement a system like that, you can at least satisfy both of those problems or both of those pulls in the industry. So I want to talk about a few association methods. The first association method, so I'm going to pause for one moment and kind of cover the processes for malware analysis. So there's a few basic kind of overarching chunks of malware analysis. So the first one is static analysis. So this is taking a file and looking at its features without actually running it or letting it do anything. So you're just looking at its static features. Kind of the next level up is dynamic malware analysis, and that's where you execute or run the sample and try to collect data on what its behavior is and what it does. And then the next one that I'm not actually going to cover in this talk is manual reverse engineering. So that's sitting there working through IDA or Binary Ninja or Hopper, and then running through a debugger, stepping through the program, seeing what it actually does step by step. So one of the important things to go for when you're first doing static analysis is collect hashes. And some of the best hashes are ones that allow you to relate malware from one file to another. So the hashes like an MD5, SHA-1, SHA-256, et cetera, those are good for making sure that the file you're looking at is not one that you've seen before somewhere else, but it's not good for finding other files that are related to it. It's actually diametrically opposed to doing that. So these are some hashes that allow you to look at the structure of a file and find other files that are similar to it. So SSDeep is context-triggered piecewise hash, aka fuzzy hash in the street slang. And so what this does is essentially chop your file up into regular pieces and then figure out piece by piece basically how different they are from another file. So what you're essentially doing with a fuzzy hash or a context-triggered piecewise hash is you have the actual file that's identical. So you have the file, and that file is identical to itself. So if you think about that as a point, you're then going to have the SSDeeps of all of these other files in your repository, and all of those are going to be points in a three-dimensional space around the point that you're looking for. And then what you want to do is you pick, I use 40, but you basically pick a threshold. And that threshold is a sphere around the point at the center. And so all of the points within that sphere are related or potentially related to the file that you're investigating. Hopefully I explained that pretty well. And then an import hash is conceptually, it's something that allows you to find related files. But what it does is a PE has a table of imports. So as a programmer, I'm not going to write my entire program from scratch. I'm going to import libraries from other open source libraries or libraries that I've written myself and stuff like this. And so the libraries that you import has an import table. And so if you take the import table and create a hash of that import table, import tables are fairly unique. There's a couple problems I'll show in the next slide about that, but that particular import table, if you find that same import table in another file, that other file is potentially related to the file that you're looking at. So an import table hash, or an imp hash, is a good way to find other files. Both of these actually have a couple of, I wouldn't call them flaws, but problems that you just need to be aware of, or weaknesses that you need to be aware of. So SSDeep, the weakness with SSDeep is typically the file that the malware library that you're looking at is filled with files that are packed. And so malware typically will will use a packer, and so the actual code that the malware author wants to execute, might actually identify who they are, might be caught by AV and stuff like that. So what they want to do is actually encrypt or compress or encode in some way that data that they want, the executable that they want to run, and they compress it into another PE file, and that PE file is packed by the packer that actually does that process. And so malware will run, and it basically runs the packer, and then it unpacks itself, and then it'll run the payload. So you can see the problem here. If you're looking at a piecewise fuzzy hash across packed malware, you're going to find that you're finding similarities among the packers. You're not finding similarities among the payloads. So import hash, this also has another gotcha that you need to be aware of. And the gotcha here is the certain types of files are going to have an identical import table. So if you've ever run across a piece of .NET malware, you'll find that that piece of .NET malware shares an import table with almost all the other various .NET files that you can find. So if you're looking at .NET malware, using the import hash is not something that you should go for. File names. So file names are fairly boring if you find exactly the same file name. But when where it gets interesting is if you can develop a regex for a pattern in the file names. And if anyone's familiar with the concept of a domain generation algorithm, the same sort of thing applies to a file. So if you have a file name that is dynamically generated on a particular machine, you can develop a regex, potentially, for the pattern of that file generation algorithm. And so that's where it gets exciting, because you can actually collect those file names and say, oh, these two might be potentially related because they're either using the same file generation algorithm, et cetera. I put this in there just because it's interesting. This is actually a side note on URL structure. So URL structure, when you're talking about malware, if it's the download URL, this is where you have the implant reaching out to grab a payload from somewhere and download it. The structure of that URL is related to the vulnerability in the CMS that was used to exploit to load that payload and then host it somewhere. So it's going to have stuff like WP admin and this sort of thing. But just think of that concept that you can actually, there is structure there. So if you think about that, you then have so this is an example of, the structure of a download URL, and that's very simple. This is super simple, just so you can kind of understand the concept of how you could write a regex to detect the different themes which are commonly exploited in WordPress. So C2 URL structure is very, very interesting, because that URL structure is decided by the malware author, and it's actually used by the malware itself. So if you use that same concept of finding patterns in the URL structure, you could match those patterns in URL structure of the C2 to various malware families, potentially. So this is actually, this is a actual malicious URL from last year, and you'll notice in the regex that there is a UID at the end. I did not include the UID in the example URL. The reason for that is because it's a base64 encoded string of the victim. So I obviously don't want to have that in my presentation, but the victim's email address. So the regex down at the bottom will find any other particular URLs that are related to this one. So this one is actually one of my friends, And I wrote a blog post about this last year about this. So this is actually hosted on Blogspot. So a little bit of a trolling title. Fancy Bear Pen's the worst blog post ever. It was basically just a redirect. So the next kind of analysis tool that you should use is EXIF. So EXIF tool gets you a variety of data. I know that it was born from EXIF data in images, but it's definitely expanded into a variety of file types, including PE and anything you can find, PDF, et cetera, et cetera. So you get a lot of good static data from EXIF. And it also can put out, can output JSON format, which makes it very easy to kind of get at the data and include EXIF tool in your tool chain. So another thing that I'm working on right now is finding code signing certificates that have been used for signing malware. One of the things that I'm looking at is gathering these and then basically blacklisting them, excuse me, and reporting them to the CAs in bulk. Because there's actually a surprising number of code signing certificates that are being used to sign malware. And the more you can actually report them, the faster they get put on the certificate revocation list, et cetera, et cetera. So the various kinds of code signing certificates you'll see in the wild. You'll see stuff that's signed by a fake cert. You'll see stuff that's signed by a real or a stolen cert. You'll see stuff that's signed-ish. It just kind of looks like signature structure, but it's broken in some way, and it doesn't actually, you can't even extract the data using typical means. You have to look at it and kind of fix pieces of it before it can even be parsed by OpenSSL or any of the libraries you want to use. So let's take a look at a piece of signed malware. This is fairly old, but it's a little bit of a famous one. So this is a known malware sample that is associated with Desaruby APT. And one of the members of my team a few years ago found that it was signed by this DTOP tools, and it's a valid signature. And so he started pivoting around across this signature in other files that were available, and found another one. So found a related sample that was signed by the same one, and lo and behold, this one is Sacula. And both of these are related to a particular incident that might be familiar to some of you. So these were some of the C2s that he found associated with that whole incident. And it turns out that was the Anthem hack. So there's another blog post you can take a look at and look at all of the processes and the analysis that was done there. So I'm going to kind of move kind of quickly through this part because this is kind of, you need to know about it, but it's kind of boring. So sections, imports, exports, resources, these are all ways that if you take hashes of them, so these are all just pieces of a PE file. So I know this is a very confusing, kind of very small slide, but it basically shows you that a PE that you execute on Windows, it has a very, very, very structured file structure. So you can take certain pieces of it and take a hash and then find out if that particular piece matches up with that same piece in another malware file. So you can use sections, take a hash of a particular section, find another file that shares that same section. Same thing with resources. You can take a hash of a particular resource, find another file that find one or more other files that have that same resource. Now, I'm going to talk to you about a couple of things that are, some proprietary stuff, but probably a lot of people have access to it. So VirusTotal has VirusTotal Intelligence, where you can submit a file, and then you can take a look at their sort of proprietary black magic of finding related files. So there's an index called similar to, and you can say similar to, and then the hash of the file you're looking at, and then it'll tell you what they think are similar to it. And then there's another friend of the family here. So Reversing Labs has another algorithm that the goal is the same thing, but they've also they've described how they do it. So they've got a blog post about like what their hashing algorithm is, how it works, et cetera. So back to the metadata. So if you're not looking at a PE file, if you're looking in the world of documents, there's lots of different data points that you can pull out. Some of the ones that I find very useful are the author. So in the Office world, that's called the author. In the PDF world, it's called PDF producer. Timestamps are also great, looking at timestamps from, also looking at compile timestamp in PE is great. Looking at language, as long as it's not English. If it's English, it's kind of like, eh. So now I want to fast forward to dynamic analysis. So I know there's probably a lot more to cover in static analysis, but this talk is not actually about static analysis, more about gathering the data and what you do with it. But from the dynamic analysis end of things, you have a mutual exclusion, so mutex, you may have heard of this. What it does in the good software world is prevents a race condition when you have multiple processes. One of them will create a mutex, and the other one will look for it, and if it finds it, won't do the thing that it was going to do, so it prevents a race condition. Same thing in threading or multiprocessing. But what malware does is kind of the same thing, but what it wants to do is create a mutex so another copy of itself doesn't stomp on it. And so when it creates a mutex, because it's a mutual exclusion, that string is many times that is a unique string. So you could see a mutex shared across various different malware files, and so that's a good way to associate them. Registry keys, of course, I think everybody knows what registry key is, but it's a hierarchical database for OS and software settings. And malware goes in there and does all kinds of stuff in the registry. Much malware does. Touching keys, reading them, writing them, deleting them, all variety of things. And so the pattern of activity that the malware does in the registry can be unique. And so if you've got a pattern of hitting a particular registry key or or doing a certain set of activities in the registry, that can be used to associate various unknown files. So I want to go into some more advanced techniques. And so this there are various clustering algorithms out there. I'm going to cover a few that are available for you to use. If you want to come talk to me after the talk, I know pretty much most of the various ones. So if we want to trade new ones, I'd love to hear about new ones. But I want to start with kind of giving a plug for Sebdraven. So this is a talk this is a class that I took at BotConf 2 years ago, December of 2017. And so it was eye-opening. It's Python machine learning, how to clusterize a malware data set. I'm not going to go and just go through the whole talk, but I encourage you, the whole talk, the whole course is on GitHub. So I encourage you to kind of step through it on your own. But I'll boil it down to, basically it uses a couple of algorithms to show you from a training set, then you can see what clusters there are among those files. And so what a lot of people think is if you're doing clusterization and all this sort of thing, we're going to need a GPU. But that is actually not correct. So I encourage you to look at that workshop, and you'll discover that there's some kind of magic that you can do with matrices that kind of save some memory and get you where you need to go without actually using a GPU and horsepower. So we got the 5-minute mark. I'm going to skip over the InfoSec finer things. So Icewater. Oh, all right. I'll just cover I'll cover the InfoSec finer things. So there's a plug for one of my colleagues. So this is wine pairings with malware research. So if you do malware research, you can follow the Twitter handle and get some wine pairings and other cheese and recommendations with malware families and have a little bit of fun. So the next association method is the diamond model of intrusion analysis. This one is quite complex, but it's also a way of basically creating groups and then associating those groups. This is, I encourage you to go take a look at the website ThreatConnect. I can show you the entirety of this discussion we had in the office. But we applied the diamond model to Star Wars, and believe me, this was a knockdown, drag-out argument in the office as to where particular things fit into the diamond model. This is the link to the original diamond model paper. Go take a look and read it. It's a very valuable methodology. Next association method is Icewater. So this is a clusterization algorithm. You can go to icewater.io/search. And what it gives you is clusters that are related using the methodology that this algorithm uses. And you'll get a cluster, and then you'll have cluster neighbors. So these cluster neighbors are either 1 or 2-bit different from the cluster that you're looking at. And so each one of the files that you look at, you can drill down into the cluster, and you can see visually visual representation of the file. You can see how many members it has and some other valuable information. There's another association method, control flow graph analysis. So control flow graph analysis, again, this is one that I defer to an expert if you watch this YouTube talk, if the camera was like a couple inches to the left, you'd see my head. I'm in the front row. But this is a very good review of control flow graph analysis. But the basics of it are you take disassembled source code and then arrange it in code blocks. So if you have disassembled source code, you have a couple of variety of ways to jump from one block to another. You can do an if-then, so it's like if, and you go here, then you go there, or you could have some type of loop. And if you take that control flow graph can be boiled down into a signature. And so if you think about it, the malware authors might reuse some of their top-level code, not in the libraries, but at the top level. And so you might be able, sometimes you can get a signature that will match across different files, and you can infer that they might be related. So this is my favorite part of the talk. This is the new stuff. Hopefully I'm not going to rush through it too fast. But if you have threat data, you should be graphing it. So I repeat that. You should be graphing your threat data. I don't disagree with people using Elasticsearch, but as you'll see in a moment, just the word that's in the name of the software is search. It's not graph. So there are better softwares out there to use for graphing and getting graph data results than Elasticsearch. I'm not knocking Elasticsearch. It has a very good skill set. So this is friend of some, enemy of others, Stix. So the Stix model. Stix model, if you look at it and think about it, it's made of 2 general categories of objects. So you have Stix domain objects, and then you have Stix relationship objects. And the Stix domain objects are related to each other by 1 or more Stix relationship objects. So if you think about it, that's a graph. That is absolutely a graph. And so what you should do is use software that allows you to graph your graph data. So if you've got Stix data, or if you've got just threat data in general, use a graph. And so what I want to cover is some of the tools that I use. So the data formats in the graph land, you have the Resource Description Framework, RDF. This is the one that I use. JSON for linking data is another data format, which you should probably decide on which one based on the graph database that you're using, and that's why I made the decision to use Resource Description Framework, which you'll see in a second. I'm going to show you a picture of JSON linking data, but I'm going to show you RDF in action. So this is basically JSON linking data. So it's a way to add some syntactic sugar, let's call it, on there to show links among data points in JSON format. But RDF, I know this is a little bit less sexy looking, but it's very powerful. So this is RDF in N-quad format. And so what you'll see here, this is actually a very simple set of graph data. Each one of those I'm just going to call it a paragraph. I don't know what the official name is for it, but whenever there's a space, each one of those blocks of text is a node. And then you'll see some of these right here. So the has file name, malware family, member of, those are called edges. And so everything in a graph is either a node or an edge. Very simple. So you've got nodes and how they're related to each other. And so what I'm going to show you here, these are some of the graph databases that are kind of the leaders in the space. Neo4j. I don't use it. I used it, but I've moved on to dgraph. Dgraph is kind of the state of the art, in my opinion. It is essentially a key value store with dgraph's database on top of it that takes that key value-ness and then adds a graph layer on it so you can do graph-type queries to it. And and it's also written in Go, so it gets the hipster points. So I wasn't sure about the intellectual property of putting a book cover in my talk, so I brought the book with me. So Introduction to Graph Theory, if you're interested in graphs, this is a good place to start. And so this is some of my current work, so working on clusterization algorithms. This and the next couple of slides are my sacrifice to the demo gods. And so these are some stills of what I'm about to show you in the demo. So this is basically a malware cluster, and the purple are members of the cluster, and then that blue one is the one that I am examining, and I've found another file that's related to it via those three tags in red. So this is a very simplistic concept here. I'm not going to go super complex. I want to show you just the power of some of the most simple pieces of doing graph analysis. So, of course, this is the sacrifice of the demo gods. This is exactly what I'm going to show you in a second. But basically, you've got the blue, which is an import hash. So I've got an import hash. I want to find things that share that import hash. So those are two files that are graphed. Now, I know this doesn't look so sexy in its still form, but give me a moment. And then you can expand the graph and find other relationships. And so this is the green in the middle is Neshta, and so this is the malware family that relates those two files together that are also related by that file hash or the import hash. So let's try a demo. Ooh, questions? That's not yet. Okay, so dgraph has an interface, graphical user interface called Ratel. And you can build your own using JavaScript libraries and such things like that, but you can get a lot of mileage out of just the basic interface. And by the way, you will see in just a second just how powerful this is, and also how much something like Maltego, you can get a lot of the stuff that you get out of Maltego just by kind of thinking about it for a little while, putting your data into graph format, and using a graph database. This is the schema. It's kind of hard to see. Let me see if I can blow it up a little bit. So this is the schema. Fairly simple. We've got file hashes, file size, file names, MD5, et cetera. This is actually the same data that we just saw in the talk over there. I've already preloaded it into the database, but I want to show you that this is one of the ways, if you're not using code, to load data or mutate it in the dgraph format. And so for the last hurrah, we're going to run a query. And so the query returned one node. So that's all I was looking for. I'm looking for the node that has this particular import hash. But dgraph, the Ratel interface, gives you some really cool features. So if I select this, we're going to see, let me back out a little bit. Ooh, that's way small. Let me just rerun that. Okay, So if I double click this, then it's going to show me all of the edges. So it's going to expand edges, right? And so then these are two files that share that import hash. Now I can expand the edge here as well. So this edge expands, and now I've got this guy, that is the malware family, Neshta. This down here is just the file name. And then over here, I can expand this one, and it will automatically connect any of the related files that are, any of the nodes that are related by a particular edge. So you can see the power here where you're actually, if you load this up with your data set and continue loading the data that you're collecting, putting it in graph format and putting it in here, you can do a lot of the things that you get out of paid software like Maltego for nearly nothing. But Maltego does have a lot of amazing features in it, but if you're just looking for some of that basic stuff, like finding a tree diagram of how things are related, and you can see the power here. So, any questions?
One.
Yes.
I've got a bunch of students who have put together a spam trap for me, and if you want to have them start with anything, is there any, to start with this process, is there any set of malware or any suggestions you have how I select the ones I want to start doing this analysis on?
So they are setting up malware spam traps, or they're?
I've set it up for them. So
oh, okay.
These phones have very interesting lives, the places they go and such.
Mm-hmm.
So are there any things we would concentrate on first? What's the first step for this?
So I would. So file types. I mean, I would start with PE files because document analysis is a little bit more complex. I would also start with less evasive malware. I can probably shoot you a list of stuff that's less evasive, but you're going to find stuff that's a little bit older. Some of the newer stuff that you're collecting now is going to be evasive, so it's going to be more difficult to analyze. And if you're setting up spam traps, I put a plug in for my talk at DEF CON 3 years ago, something like that. Just look up spam honeypots. Should be a review of how to set up spam honeypots and how to get good results. Yep. I have the luxury of being an independent malware researcher, so I don't have to deal with network pipes.
So the question I have is, when you're dealing with classified networks, a lot of your malware you see on a classified network is some form of APT.
Mm-hmm.
You can't really put that into the public domain looking for comparable indicators because that could tip your hand. What do you suggest to do with that kind of data inside of that network, knowing you don't have the same level of accessibility and community intelligence?
So the question you're asking, let me kind of rephrase it so I see if I get it right. So what you're asking is, if you're on a classified network where you're compartmentalized and you don't have access to, I would say, a malware repository out on the internet, right? Well, I don't know how to solve that problem for you, but if you get that collection of data inside, you can apply all of the techniques that I've been talking about. So I'm not sure how to get out to data sets that aren't on your classified network. Was that your question?
It's just that you can't necessarily. So when I was at State Department, I had crawled virus book, which apparently is not a good thing. And I've done it regularly to build internal hashing mechanisms.
Naughty, naughty.
But where I'm headed now, that's not a luxury that's available.
Yes, I think there might be, so if you have at least access to the data, and I don't mean VT, because you're gonna have, you would have API access to look at the data, but you wouldn't actually have the whole data set. But if you've got a whole data set, and you don't have room for it somewhere else, you can always use, I mean, your mileage may vary, but something along the lines of a Bloom filter might help you, you know, at least make it more efficient.
The hashes themselves would be.
Yeah, but you'd have an incredibly large data set if you just have the hashes. That's where you'd use a Bloom filter to kind of, yeah, cut down on the. All right, thank you.